अपने इंट्रोडक्शन से शुरू करूँ कि आप लोग? सही है। सबसे पहले अस्सलाम वालेकुम अगेन। मैं डॉक्टर हैदर लतीफ़ हूँ। मैं डेनमार्क में होता हूँ। लास्ट फॉर द पास्ट 8 ईयर्स मैं डेनमार्क के अंदर हूँ। मैं मेरी जर्नी जो है वो स्टार्ट मैंने पाकिस्तान लाहौर से मैं बिलोंग करता हूँ। आई बिलोंग फ्रॉम लाहौर। यहाँ पे मेरी इनिशियल आई हैड ओ लेवल्स फ्रॉम एचिसन। फिर उसके बाद वेंट टू गवर्नमेंट कॉलेज यूनिवर्सिटी। आई हैड प्री इंजीनियरिंग एंड देन आई वेंट टू यूटी लाहौर। वहाँ पे मैंने मैकेनिकल इंजीनियरिंग की। मेरा बैच था 2013 टू 2017। सो उधर फिर मैं देयर वाज अ सोसाइटी कॉल्ड ASME, अमेरिकन सोसाइटी ऑफ मैकेनिकल इंजीनियर्स। तो 2016 जब मेरा फाइनल ईयर था तो आई मेट विद रमजान साहब फर्स्ट टाइम। तो ही वाज इंटरेस्टेड टू हैव एन चैप्टर HVACR का चैप्टर इन यूटी लाहौर। तो तब हमारा फर्स्ट इंप्रेशन हुआ। ही स्पॉन्सर्ड वन ऑफ द इवेंट्स। तो वहाँ से मेरा इंटरेस्ट डेवलप हुआ HVACR का। आई हैड नो आइडिया व्हाट HVACR इज। तो मेरा था शुरू यूटी लाहौर के अंदर मेरा था कि आई विल आइदर चूज HVACR in as a my core field, or I will choose power, because UT Lahore was very popular for power. तो eventually I just chose HVACR। और मैं फिर UT लाहौर से फारिग हुआ 2017 के अंदर। और मैं थर्मल पावर इंजीनियरिंग UT लाहौर के अंदर ही मैं हो गया, इनरोल्ड हो गया एज ए मास्टर स्टूडेंट। और साथ साथ मैं डेस्कॉन के अंदर जो था HVACR के प्रोजेक्ट्स करता रहा। और यहाँ पे हैं शहजाद साहब हैं CDC। पहले उनके पास होता था ACS इंजीनियरिंग कंसल्टेंट। तो मैं उनके पास भी जाया करता था क्योंकि मेरा मास्टर्स का प्रोजेक्ट जो था, बिकॉज आई ऑलरेडी चोज के आई विल बी वर्किंग इन फ्यूचर इन HVACR। सो मैंने फिर रमज़ान साहब जो थे उनके साथ अफिलिएशन रही, फिर शहजाद साहब के साथ रही, फरहान जफ़र थे एक हमारे सीनियर थे, उनके साथ रही। तो इनके साथ काफ़ी अच्छी रही। तो प्रोजेक्ट्स पकड़ता रहता। तो फिर VRF सिस्टम का मुझे वहाँ से पता चला। आई डिडंट नो एनी आइडिया। मैंने अपना प्रोजेक्ट जो था जो मास्टर्स थीसिस का प्रोजेक्ट था उसके ऊपर VRF सिस्टम के ऊपर किया। यूटी लाहौर के अंदर यूटी ऑडिटोरियम जो है ना वो काफ़ी बड़ा है, उसके अंदर चिलर सिस्टम लगा हुआ था। तो वी ट्राइड, इट वाज जस्ट एन फनी आइडिया कि वी विल बी हैविंग VRF सिस्टम ऑन ऑडिटोरियम इंस्टेड ऑफ चिलर सिस्टम। तो एक एक्सपेरिमेंट किया। VC साहब जो थे उन्होंने काफ़ी ज़्यादा अपलोड किया कि इट कैन सेव सम एनर्जी एंड समथिंग लाइक दैट। और 2018 के अंदर मैंने मास्टर्स कर लिया और थर्मल पावर के अंदर। एंड देन आई गॉट अ फेलोशिप। मैं यूटी लाहौर के अंदर हो गया एज अ लेक्चरर। और 2019 फ्रॉम जनवरी टू 2019 अगस्त आई स्टेड एज अ लेक्चरर इन यूटी लाहौर। और फिर मुझे फेलोशिप मिल गई डेनमार्क के अंदर। और I went to meanwhile I was also running my own consultancy, small sort of HVAC। एक काम मिल जाता था, शहजाद साहब से थोड़ा काम मिल जाता था कभी। एक थे सजाद हैदर साहब थे। और ऐसे थोड़े थोड़े काम पकड़ता रहता था HVAC के। तो मैंने नेशनल इंक्यूबेशन सेंटर था लम्स के अंदर, एहसन इकबाल ने शुरू में शुरू किया था। इट वॉज लम्स एंटरप्रेन्योरशिप। तो वी इट turned into national incubation center. So I'm also graduate of that. So I introduced CFD, computational fluid dynamics, into ventilation. तो हम यहाँ पे यूज़ करते हैं हैप और मुख्य सॉफ्टवेयर यूज़ करते हैं। हाँ, तो वो अर्ली एनालिसिस प्रोग्राम इट्स वेरी कॉमन। इवन टर्की में और ऐसी जगहों पे काफ़ी सॉर्ट का इवेंट होता है। उधर से मुझे एक प्रोफेसर मिले थे और उन्होंने मुझे कहा था कि CFD इज़ अ वेरी यूजफुल टूल। तो वाई नॉट डिज़ाइनिंग HVAC थ्रू CFD? I'll be selling HVAC, but it through CFD. So this was an idea. तो I enrolled myself as national incubation में। मैंने लम्स के अंदर किया। लम्स का ग्रेजुएट हूँ मैं, 1 साल उधर रहा हूँ। फिर मीनवाइल मुझे फेलोशिप के लिए चला गया डेनमार्क 2019 सितंबर के अंदर। वहाँ पे डेनिश इनोवेशन फंड था, उसने मुझे स्पॉन्सर की। इट वाज एन इंडस्ट्रियलाइज PhD। लकीली जो मेरी PhD थी वो जो मेरा VRF सिस्टम था उसको डेनमार्क के अंदर कहते थे एक्टिव चिल बीम सिस्टम। और आई डिडंट नो दैट इवन व्हेन आई वेंट देयर। वहाँ पे जाकर मुझे अंदाजा हुआ इट्स द सेम सिस्टम दैट वी, बट दे कॉल इट एज एक्टिव चिल बीम सिस्टम। तो एक कंपनी थी लिंडअप। लिंडअप इज़ अ वेरी फेमस स्कैंडिनेवियन कंपनी एंड इट मेक्स डक्ट्स, लेकिन along with ducts it also makes some systems. So लिंकडअप और डैनिश इनोवेशन फंड ने एक प्रोजेक्ट स्पॉन्सर किया। वो अभी आके आप लोगों को बताऊंगा। काफ़ी इट वाज वेरी इंटरेस्टिंग। स्टिल इट्स गोइंग ऑन। आई एम राइट नाउ पोस्ट डॉक रिसर्चर अभी भी मैं उधर हूँ। मेरी फंडिंग तकरीबन अगर आप तकरीबन 2.5 मिलियन डेनिश क्रोन की। तो वी डेवलप Scandinavia's precision ventilation strategy. It is the first ever वेंटिलेशन स्ट्रेटेजी जो मेरे नाम से, ये प्रिसीजन वेंटिलेशन मैंने ही नाम दिया हुआ प्रिसीजन। एनीवेज मैं एक्सचेंज पे चला गया ओक्लाहोमा स्टेट यूनिवर्सिटी में। 1 साल मैं उधर रहा हूँ यूएसए के अंदर। ऑटो मॉन्स्टेड फंड था जो मुझे अलॉट हुआ, मैंने विन किया, और 1 साल वी स्टेड इन ओक्लाहोमा स्टेट यूनिवर्सिटी। इट वॉज कोविड टाइम्स, वेरी डिफिकल्ट टाइम। कोविड के अंदर जो था, इट वॉज आई मीन it was not laboratory work, but it was more CFT. So I did simulations and all this stuff. In 2022 and 23 कोविड, पोस्ट कोविड, मुझे मेरे प्रोफेसर ही जो था जिसके साथ मैं पीएचडी कर रहा था, डॉक्टर अली रजा अफशारी नाम था, ही इज़ अ वेरी फेमस नेम इन इंडो क्लाइमेट। ही हायर्ड मी एज अ रिसर्च असिस्टेंट। और उसके बाद मुझे एक सबसे बड़ी ग्रांट है होराइजन, होराइजन यूरोप, अभी लम्स को मिली है। लाइक इट्स द फर्स्ट कंट्री इन एशिया, फर्स्ट यूनिवर्सिटी इन एशिया जिसको मिली है होराइजन। तकरीबन 52 करोड़ रुपया मिला है लम्स को। तो होराइजन हमें मिली, हमारे ग्रुप को मिली। होराइजन और इनो एक्सप्लोर और इनोवेशन फंड, 3 फंड्स मुझे मिले रिसर्च असिस्टेंट के तौर पे। तो दैट लेड मी टू हैव अ पोस्ट डॉक टू। तो फिर मैंने पोस्ट डॉक स्टार्ट की, और अब तक मेरे पास पोस्ट डॉक है। तकरीबन ये 4 साल का प्रोजेक्ट था। इट हैज़ बीन लाइक 3 years नाउ। और मेरी फंडिंग है, इस वक्त मैं इधर हूँ पिछले 6-7 महीने से ड्यू टू सम फैमिली रीजंस। तो वो, लेकिन मैंने 2 रिसर्च असिस्टेंट्स वहाँ पे हायर कर आया हूँ। लेकिन मैंने फिर ड्यूरिंग 1 year ऑफ माई PhD आई आल्सो वर्क एज CFD स्पेशलिस्ट कंप्यूटेशनल। रेंसर एक कंपनी है, उनके साथ मैं एफिलिएटेड हूँ। अब वो कंपनी का जो फाउंडर है मैथ्यू जॉनसन, ही इज आल्सो रन 6 more कंपनीज। ही इज अ साइंटिस्ट, अ वेरी फेमस साइंटिस्ट। ही आल्सो रन द कंपनी कॉल्ड एम्बिएंट कार्बन, और उसका भी मैं अभी कंसल्टेंट हूँ, साथ चल रहा हूँ। तो एनीवेज पोस्ट डॉक्टरेट का जो है वो एक्सपीरियंस ये है कि अल्फोर्स के एक्सप्लोरर 2 फंडिंग्स है मेरे पास। इसके अंदर हम डैम्पर्स के ऊपर, जो हमारे डैम्पर्स यूज होते हैं HVAC के अंदर, और जो सेंसर्स यूज होते हैं, वी आर डेवलपिंग द स्मॉलेस्ट सेंसर टू मेजर द एयर फ्लो, सो दैट देयर इज नो प्रेशर ड्रॉप लॉसेस। हम इसलिए एयर वेलोसिटी के लिए, तो हम देयर इज अ कंपनी कॉल्ड नेक्स्ट वेंट जो मेरे अपने प्रोफेसर की है। वी आर पैटेंट, हम पैटेंट उसका रजिस्टर कर रहे हैं। तो इट्स अ वेरी इंटरेस्टिंग प्रोजेक्ट टू। और मेरा फेमस कोर्स है काफ़ी, पीटर वी नील्सन, ही इज़ अ वेरी big name in CFT in building ventilation. He introduced CFT in building ventilation in 1980 when he was in Boeing. So I and he actually organized a course called Advanced CFD in Building course. ये गूगल पे अवेलेबल है, आप लोग देखें। अभी मैं लेकर आया हूँ अभी मार्च अप्रैल मई के अंदर डेनमार्क में। तो इट्स अ PhD कोर्स फॉर द PhD स्टूडेंट्स। So anyways, this is my introduction. Still I am in Pakistan. I am in Pakistan. मैं अभी लम्स के अंदर 2 दिन होता हूँ। असिस्टेंट प्रोफेसर भी हूँ यूनिवर्सिटी ऑफ लाहौर के अंदर। और मैं उकाड़ा यूनिवर्सिटी के अंदर भी हूँ, डायरेक्टर एकेडमिक्स हूँ। तो काफ़ी चीज़ों में इन्वॉल्व हुआ हूँ पाकिस्तान के अंदर। तो क्योंकि यहाँ पे मैं काफ़ी चीज़ों में इन्वॉल्व इसलिए हूँ क्योंकि इवेंचुअली it's very few people, but I plan to return to Pakistan in future. You should. This is why I'm just creating a field. I am creating a field for myself over here. So I'm just here. मैं sabbatical leave, आप लोगों को पता होगा sabbatical leave मिल जाती है, 5 साल आप डेनमार्क में रहें, लम्स के अंदर भी मिल जाती है। तो मैं sabbatical leave लेकर आया हूँ 1 year की। तो मुझे ये था कि मैं देखूँ पाकिस्तान का जाकर what's new in Pakistan and what's happening in Pakistan। तो अल्हम्दुलिल्लाह काफ़ी अपॉर्चुनिटीज़ हैं। I didn't find out खुद आई हैं opportunities. So if someone says that there is no opportunity in Pakistan, there are opportunities in Pakistan if you are a hard working guy. So anyway, this is an introduction. मैंने पाकिस्तान में कुछ नहीं मेंशन किया इधर, लेकिन it's the thing. जी। तो बिस्मिल्लाहिर्रहमानिर्रहीम। टॉपिक जो फॉर टुडेज एक तरह का लेक्चर जो था, the basic objective was कि I gave a sneak about the Danish perspective of ventilation, कि डेनमार्क के अंदर, स्कैंडिनेविया के अंदर वेंटिलेशन प्रैक्टिसेस क्या होती हैं। क्योंकि अनलाइक इन US से जो पाकिस्तान के अंदर काफ़ी प्रैक्टिसेस हैं, यूरोपियन प्रैक्टिसेस आर स्लाइटली डिफरेंट फ्रॉम अमेरिकन और स्पेसिफिकली पाकिस्तान, और ये जो रीजन है मिडल ईस्ट जो है, इसके अंदर स्पेसिफिकली थोड़ी डिफरेंट है। So the topic I will be presenting here is precision ventilation in open plan offices. It's a study of variable jet interaction between active chill beams. So I'll start with a very basic question. how are you feeling right now? This is the question that I usually ask, because my strategy that I actually gave in Scandinavia is basically it revolves around this question. For example, if I am wearing right now, you have seen that I am wearing a three-piece suit or two-piece suit, so I am feeling a bit warm, and maybe someone who is wearing a just t-shirt or something that, and maybe someone who actually came from an exercise, or maybe someone who came um, from something from, he's sick, maybe he's not well, feeling well, so he has a different level of thermal comfort as compared to the person who actually is completely healthy. So if I just ask maybe a student that how you are feeling, so he will be saying warm, and maybe if I'll ask someone else, he will saying I'm feeling a bit cold, or a bit less warmer than him. So this question actually says a lot. It says that uh, everyone has a different level of thermal comfort. So in research, in while doing research or while finding the gap of research, we usually go for the problem. What's the problem in the world is happening right now? We have air conditioner at the moment in our building, in our room, so you know that we'll just set 21 degree or 26 degree, and everyone will have to be at the 26 degree. This is the thing. But everyone doesn't have a same level of thermal comfort. This is another thing. Everyone has a different level of thermal comfort, so this is a problem. So everyone's thermal comfort should be addressed. This is a problem. So the office occupants, basically this whole research is basically the foundation of whole research is based on the offices. Let's forget about residential buildings at the moment for next half an hour or an hour. Just talk about offices. In office building, there are different people that work. Different have different genders. They have different level of metabolism. They have different level of clothing habits, and everything is different. So everyone will have different level with which he will get satisfied with the indoor environment. So um, the problem, we just diagnose the problem that everyone has a different level of thermal comfort, and this is due to the change in metabolic activities and clothing. And usually the controlling factors that we designers, we actually see engineers, we actually people, what we can control only air velocities, temperature, humidity, and all those things, right? And this is actually, we are just talking about, just forget about system, we are just talking about indoor climate at the moment. So how about if we provide a new system that has air velocity with the different metabolic rates? For example, it's a very everyone has different. If I'm fat, I will have a more metabolism. Maybe you have a metabolism rate 1.2, I have 1.6. It's a metabolic rate. I have more heat emission. So but our system is not designed like this, right? So in Scandinavia, we carefully think of these things. Like for example, if you are not feeling comfortable, this means that your productivity will be decreased. You are not well with doing the functions. So we have to make sure that your productivity is raised. So we have to provide individual thermal comfort. So this has been the problem, and this has been a wild idea. In 2019 when I came, we had a research, we had a proposal, and this was the strategy what we gonna do. So before we had an objective. So the objective of this work was actually develop a new way. In I just tell you for the information that in Scandinavia, active chill beam is the only or maybe the most commonly used HVAC product. So active chill beam, over here I will be referring active chill beam means ACB. I can abbreviate, or if you just don't have understanding, so I'll be using active chill beam as a whole. So active chill beam is the most common used product, right? And we had a collaboration with a company called Lindup. So we had developed an R&D system that we should develop some system like this, like cassette, that it has some variation in the system that can provide individual thermal comfort for office people, for office guys. So this was first objective. And then this was only for the two people maybe sitting in the room. For example, one person, one device doesn't problem, like he can change the system. But if there are more number of people sitting, so then there is a problem that there are jet collisions that are happening, and then they are coming down, and then we have to move those. So there, for multiple, we had that. For large offices, we have high-speed cooling jets that will be coming from the ceiling towards the occupied zone. We have to use that, and we have to create microclimate for the people in the offices. It's a very, very new and very novel idea for conducting. And of course, when we write, as a researcher, we write proposals, we get grants. The reason for those is we save energy. So saving energy is one of the things. If like as an engineer, if you say to your customer that you can save energy up to 10%, it's a lot. So, but I will just tell you before doing this, this system is not specifically for saving energy. It is very funny that if we just increase the temperature from 24 degree to 26 degree, it will save energy. This is obviously, but this is for actually having an individual thermal comfort for the people. This system was designed. So how individual thermal comfort for only thermal comfort. We are not talking about air quality at the moment. So we had this research. We had this research for almost 5 years, and we had a lot of publications out of it, a lot of patent out of it, and we also had some. There are 9 buildings in Scandinavia. Two or three of them are in Copenhagen. 4 of them are in Lund. 6 of them are in Stockholm area, outer area. So there are 9 buildings that have this strategy. I will in this research, and I'm sharing with you what we did actually, how it was started, how I came, and now how it is being done. So this is a research I am seeing in front of me that has been a new thing. So these first 4 were journal papers, and the next 4 was there is a very famous AHR Expo happens every year in ASHRAE AHR Expo. I have been to every year almost there, like in Nevada, in Colorado, all this, and we have been like selling this for long. So so this has been happening. We have been presenting our technology. So just an outline, quick outline. I just will not go in detail over here. Introduction, I'll just present over the individual level why it is necessary. By the way, I have just given a sneak already. Methods we used to prove this technology. A bit of background, which system we already have, and what system we actually designed, which changes we actually brought in this system, and then we leading to results and conclusions, of course, to answer the research questions we actually had. So these are some of the words that we'll be using. I just tell you, open plan offices is not very common. I think so in Pakistan. In Pakistan, mostly we deal with our own offices. Like everyone has its own office, but in outside, in I think so in Scandinavia, we even the professor and the junior researcher are sitting across the table. So it's just like an open plan office. Yes. Yeah. Yeah. So it's not mine. ये मेरा नहीं है ऐसा नहीं, लेकिन मेरी तो ये कुछ वर्ड्स हैं जो बेसिकली मैं बार बार रिपीटेडली यूज़ करूँगा फॉर अंडरस्टैंडिंग। ओपन प्लेन ऑफिसेज जो है ना वो होते हैं, उनकी आगे डेफिनेशन मैंने प्रमोट की हुई है कि ओपन प्लेन ऑफिसेज इन्वॉल्व एब्सेंस ऑफ पार्टीशंस, कि हमारी पार्टीशन जो हम डिज़ाइन करते हैं यूजुअली पार्टीशन नहीं होती, हमारे अक्रॉस एक और डेस्क होता है और हम आपने सामने बैठे होते हैं, और बिटवीन वर्क डेस्क और वर्कस्टेशन हुज आउटर बाउंड्रीज डू नॉट रीच द सीलिंग, of course, there. So this is a standard definition of open plane offices. Open plane office आप लोगों के सामने picture. I just giving you that they are why they are used in order to make more the office environment more economical. क्योंकि everyone cannot afford to give another office space. Meter square हर किसी को इतना ज़्यादा नहीं मिल सकता. So they are almost 20% more economical than traditional offices. और असल में ये रिसर्च थी. आई जस्ट टेल यू वेयर इट स्टार्टेड, एवरीथिंग स्टार्टेड. आई जस्ट have maybe 3 or 4 minutes of story that I will tell you. In 2002 and 2003, because everywhere there was open plan offices already there, but so people decided that everyone has a different level of thermal comfort. So National University of Singapore and Denmark Technical University, there are 2 universities, they started this research. It's called as personalized ventilation systems. Ventilation over here doesn't mean ventilation. In Scandinavia, the ventilation means air conditioning also, right? So I just tell you, ventilation is everything. So they said that why not we just introduce some systems that are individually controlled. So they introduced personalized ventilation systems for the open plan offices, but they got flopped. The reason was that there were large number of air terminal devices around them. I'll show you around the background of it. But open plane offices are all systems in Scandinavia designed according to the open plane offices. So thermal comfort according to ASHRAE has a very standard definition that anything that satisfies thermal environment, the guy who we actually sitting, that satisfy is accessed by the subjective evaluation. So it's the standard definition of ASHRAE. There are more than one definition of thermal comfort. In Scandinavia, according to European standards, the thermal comfort definition is different. So this is a standard definition of ASHRAE. It depends upon environmental factors and personal factors. It actually air velocity, air temperature, radiant, and humidity. They are the four environmental factors that we can control. Another one is the personalized factors that are metabolic rate and clothing insulation. So over here in research, what we cannot control everything, of course, but air velocity and air temperature were changing. We just kept radiant temperature and humidity the same, and the metabolic rate, personal factors, were the ones that we were taking into consideration, not the humans insulation. Because when we do carry out research, we carry out experiments, we have to calculate how much heat release is coming from each person and how much heat release is coming from each dummy or each body that is actually in the laboratory. So metabolic rate, we usually, I know that in Pakistan, I can frankly say that in Pakistan there is very less, maybe I'm wrong, there is a very less concept of thermal comfort. At least when I was there, when I was designing some systems. So I don't want to name, but there were some people who actually were teaching me. They used to say that add 10%, 20% tolerance into that, because over here air conditioning is like ठंड लगनी चाहिए. This is the thing. So I think so. It makes sense. Like people like in my home, nobody cares about thermal comfort. They care about ठंड लग रही है कि नहीं लग रही. So thermal comfort is a very important thing. It increases your productivity. Even the sleep, if you are sleeping, if you are have a very optimal level of temperature, so you can sleep well. It can disturb your sleep. So thermal comfort is very important thing, and for that, controlling that, we need to know the metabolic rate. We need to know the activity levels, and of course, while using HAP and all this, we add activity level over there. I know that, but this is the research behind it.
Taking 400 BTU.
Yeah, for a person, like for example, for cinema, for if you are designing for cinema, for you are designing for some playful activities, you have a different level of air. So that makes sense. But we are very strict towards the metabolic rate right now. So metabolic rate varies. These are the people. If someone is standing, he has a different level of thermal comfort. I have a different, and you have different. Who is sitting, actually?
Every individual also has a very different.
Yes, because it also, this is why it also depends upon, I have a next slide for that. Everyone has the genes also matters, even, right? Even my mass matters. If I'm a fat, if I'm whatever, even gender matters. I mean, usually males feel, I mean, it's a fight everyone between husband and wife often, that you have to keep the air conditioner on or off. So so my system actually also can resolve the conflicts. So if it works. So I mean to say that office workout, everyone has a different level of comfort and every different level of metabolic rate, actually. So factors, there are some factors that affect, of course. There are some research behind it. Studies engage gender differences, of course. Metabolic rate, with females having up to 30% lower metabolic rates than males. This is the standard research I'm talking about. Then while walking, you have a metabolic rate of 3. I told you that 1.2 is considered as very normal one. 1.2, 1.8 is the person who is actually maybe also standing and just walking around and then working. So metabolic rate varies. Then ethnicity, again, ethnicity, when someone who is from American background and someone who is from Pakistani background, even ethnicity matters for the metabolic rate. So Chinese people showing metabolic rate is up to 15% less than the Western population. So it is actually the thing that varies. So, but we don't control the parameters according to, we don't design HVAC system according to that. So this was the point. So this is being discussed, factors affecting metabolic rates. So this is actually in pictures to make students see that this all things actually matters a lot. Then there is some very boring slide, maybe because it's a very but I have referred some research over here that usually while designing HVAC system for indoor climate, we keep temperature velocity around a person like who is sitting 0.15 meter per second, 0.15, 0.25. Ashtray says up to more, a bit more. So there we say relative velocity. So we have a different, but there have been a lot of research where we increase the temperature of the room and also increase the air velocity. Why we increase the air temperature? To save energy. Like our government, often we buy air conditioners right now, everyone there is written 26 degree. This is the logic behind is that we are saving energy.
Evaporating cooler, sorry for that.
In the for evaporative cooling we are talking, yes, yeah.
Designed
For indoor climate we are just keeping the temperature high so that air velocity is increased and we save energy. And for my calculations, these are my calculations that I have done at the last. For single degree raise in temperature from 25 to 26 degree, we can save up to 5%. And believe me, I have tried at my home. I have I have air conditioner. I have asked my family to use 26 degree, and then I did an experiment 1 month before, 24 degree, 25 degree, and I just saw my bill. Believe me, it was like 5% or 4%, 3%. It is actually true. So this is another thing, but we have to maintain the level of thermal comfort, and we have environmental factor air velocity that control actually. Anyways, so this whole research actually, I just experimental study had reported 90 to 100% of thermal comfort satisfaction, even increased air velocity. So it's a good thing, it's not a bad thing. But maybe we will discuss, maybe we have some people coming up, they will be talking about draft. There is a thing called draft, maybe, and draft involves higher air velocity. If there is a higher air velocity, then people make it feel uncomfortable, but we have a solution for that too. So there are two systems basically based on, if we just forget about a all water system, air water system, all air systems, there are different categories of ventilation, air conditioning. In Scandinavia, where we are very concerned about indoor climate, in indoor climate, there are two types of ventilations. One is through ceiling and one through floor. We just don't make it very complex. So the one through the ceiling is called mixing ventilation. That is this one, 100%. It uses the Counda effect. I mean, the air is along the ceiling. It doesn't come directly because it causes discomfort. It comes along the ceiling and it gets attached to the ceiling through the pressure difference and then comes towards you. This is, and in what we say, in displacement ventilation, it is through down. But mostly the cooling is achieved, if you talk about cooling, is achieved through mixing ventilation. The reason is that because the density of air, cold air, that actually comes down, and the hot air, it comes up. So it's a natural process. So so this is divided into two: displacement ventilation and mixing ventilation. I'm just giving you the background, what is happening, and then what changes we are bringing. So there, now we will just talking about mixing, nothing about displacement. Mixing ventilation, there are two main evaporators or more devices that we actually use. One is passive chill beam, another one is active chill beam. Passive chill beam actually, as the name says, that it is through natural convection. Nothing blower, nothing, and it takes a lot of time. Active chill beam involves also air. It's all air system. Air water system. It also involves air. It also involves water. Water is a system because only air cannot do anything because of the specific heat of water is quite high. It is more powerful than air. So active chill beam. This is why used around everywhere in Europe, especially in Scandinavia, and this the principle is very common. This why this is more successful. We also now talk about this over here too. Induction. Induction is something, the air that is going into the system. For example, we just talk about outlet, that the air that is going out, that is through energy mass equation we can calculate that. But on the other hand, we'll talk about, in order to increase the performance, enhance the performance of the system, like for chill beam, there is a process called induction. We don't care about that thing, even though induction is not very low. We just have an example, if I can just give it to you, like we can just हम सिर्फ अगर फूक मारें अपने हाथ पे, तो it is quite, you can feel, if you can just see by yourself, if आप अगर आप suck कर रहे हैं, ऐसे कर रहे हैं, there is no air that is. So this is how induction is. So one part by five parts, it's the air that is coming out and one part is going in, but it can save up to 10% of energy. This is the point. This is why active chill beam is very successful in Europe. Another part why active chill beam is so much popular, when you are designing a building, it has a very it carries very low volume. The active chill beam, it's a very smart product. It's not very big product. So when you are calculate the overall volume of the building, the volume of the building, if it is decreased because of the placing this, so it also saves a lot of money. So it is economically it is very good. Through efficiency it is very good. It cools in a very good way. It has water as a medium, so it's a very successful product. But due to condensation and some of the other parameters, it actually is also discouraged sometimes. Especially humidity, condensation rate achieves this because it also has a tubes that actually, and many of the active chill beam doesn't have what we say evaporating pan. There is a pan, drain pan. They don't have it. So anyways, if we just talk about, this was actually the other side of industry, but if we talk about research, active chill beam, this paper, I have a paper on it. It's a performance of evaluation of active chill beam for office buildings, a literature review. This was my first ever paper in my life, and this was a literature review. This was, I actually had it while COVID. And these people actually who helped me writing this paper, it's a very famous paper on active chill beam. This was the novelty of this paper was, this was the first ever paper on active chill beam. There was no other review paper, I mean, on active chill beam. So this guy, the second author, who is Joran Hultmark, he is the founder of active chill beam. This man, on Lindup, the company who invented active chill beam, he was the R&D head of that company. Induction, that is happening. Induction was very familiar with everyone. Induction was happening everywhere in the world, but induction in this was not happening before. So he utilized induction, and he stressed that induction is very important. Actually, induction, the heat that is going from you to the system back, so that also creates a lot of influence on the performance of the systems. So we had a paper, we had a review paper, we studied active chill beams, and because it was necessary for us, now we have to bring innovation back to the point one, that now we have to create individual thermal comfort for the people. This active chill was creating uniform, but now we will be creating something different. These are the systems that I've talked about. National University of Singapore and also Denmark Technical University studied this system for almost 15 years. This is called as personalized ventilation system. This problem that I was talking about is actually not a new problem, it's an old problem. So they decided that why not we create for an office environment number of air terminal devices around the seating, around the people. For example, this is, you see, office environment, someone who is sitting. So what they did, everyone has different level, so they created heated chair. It's a funny like thing, but this was just talk about 20 years before. These were things that were new. uh, Ceiling, like a desk fan, right? There were a different sort of air terminal devices that were around to create a microclimate around the body, around the desk for office environment. So these personalized ventilation systems provide individual thermal comfort by using variety of air terminal devices around, and to increase energy savings, and also to create microclimate for each workstation around. So these were already being practiced, like they started. And if you just look at, if you just on the Google Scholar, if you just type the name personalized ventilation systems, so you will just find the research from 2002 to 2017, a lot of research, and you will see the professors over here, they will have a huge impact because this was the research. But this is very important actually, because the role of air terminal devices, like if it is fan, if it is a heating chair, if it is number of fans, if it is even some more, like there were even foot fan, there were vibrators, there were different things that are around the desk who were creating a microclimate. It was very important, air terminal devices. So I wrote another paper because we were addressing the problem. I wrote another paper that was a conference paper we actually presented at South Korea in 2020, and this was actually design strategies for increasing the thermal comfort and cooling demand. This was actually the review how many air terminal devices are used. I was identifying the problem. I just tell you, because of the people who maybe want to do PhD, I mean 70-80% of the PhD is finding a problem, and rest of the 25% is the solution. You already will find the solution as a researcher, but the problem is the main thing. So I wrote a paper. These are my results. So I identified that there are a number of air terminal devices around a person, right? And these air terminals, sometimes there are more than 3 for one person. Sometimes there are 2, sometimes 4, sometimes 1, and something like that. But but some few things that actually they were saving a lot of energy. But I have a question, like, is it possible, like, still, do you see these such systems around the world at the moment? No. The reason is that, especially in Scandinavia, why they got failed. This is a question. Like 15, 17 years of research got failed. You cannot see in practical in commercial buildings. The reason was architects.
Yes.
Interior. It doesn't suit. Like in Scandinavia, you care, you know, the Scandinavian design, they care a lot about interior designing. So, and you know that we all know that we get most of the projects from architects, like they refer and they all these people. Yeah. So architect, if it doesn't recommend this, so why would I just have it? This is one of the, it's all over the world, it's not only Pakistan. So this actually systems have a problem with the aesthetic was not good. The systems, like having 2 or 3 fans around the desk, it just spoils away the interior. So they were rejected. I mean, this was psychologically or all this stuff. So then we have some research questions. We created a problem that these systems are failed. We have this problem. Then we devised some research questions that we have to solve through my thesis or my research. So one of the questions was, can active chill being create microclimate by creating airflow along the ceiling, not over here in fans? Like the same system can create microclimate or not? This was the first research question. Then there was, can we have, if we have different metabolic rates, if the people have different level of heat release from the body, can their thermal comfort can be maintained at the same time through different air velocities around them? This was another question. Then there was, is there a room size, number of active chill beams occupants actually have an impact on this system or not? This was another. What will be the effect of variable air velocity zones on the vertical and horizontal temperature asymmetry? This is another one. Like we are sitting, often we see that our hand is cold and our feet is fine. So this is actually discomfort. This is, we consider it as a discomfort. This is because of indoor climate. It comes under indoor climate. अगर आप सोए में आपके कई दफ़ा पाँव ठंडे हैं और आप लोग, आपके हाथ या आपका सर जो है गर्म है, तो it is basically a health problem. It causes health problem. It will not allow you to sleep well. In Pakistan, we don't consider it a problem, but it is a problem. So will it affect the temperature symmetry or not? This was another research question. Then how much maximum air temperature I will take and air velocity I will increase will have an impact, and how much energy saving it will have. So these were the research questions that we had, and then we decided to term it that we will introduce a new strategy. We will be forgetting about personalized ventilation systems. We will be introducing new system called as precision ventilation. This precision ventilation was created by me. I actually have, there are nine buildings in Denmark, in Scandinavia. They are being installed with precision ventilation strategy. There are 2 patents that are on this precision ventilation, active chill beams, and we actually created innovation inside the chill beam. And what was that innovation? The concept was that if this is an ACB unit at the ceiling, and you see that both of the people have different level of thermal comfort. You can see that one is having a heat coming out of the body and other one is just sitting. So but if we have more air velocity toward this side, so maybe more heat will be released from that person and it will create a microclimate along that person, and both will are satisfied with the environment. Similarly, if there are a number of air terminal devices, so we have to consider jet collisions. So we have to make use of jet collisions around the room. For example, if there is this chill beam and then there is another one. So while designing, usually we don't consider it that there is also a problem of jet collision. There will be a jet that is coming along the ceiling. There will be another jet and it will be colliding. It will be coming down, and it is coming down on a person. It will, maybe he don't want that air velocity. So we can move that air. How it is possible? Similarly, for bigger offices, for open plane offices, where there are multiple air terminal devices, same will be different level of microclimate will be created. But how it will be created? This is how the methods I will be just telling. This was the normal active chill beam that I showed you before. We decided, instead of nozzles, we decided to add this thing into that. This is called as jet cone. Okay, this has several numbers on it. It has number from 0 to 9, and then you see on the right side, it's the property of Lindup. We were working with this company, the same thing. And then we have a jet cone system instead of nozzles that can move around on their own through the mobile application, right? uh, you see over here, mostly it's nozzles, right? But we added this new thing. It was not a very complicated innovation, but it was the use of thing, right? And this thing was added into this chill beam, and it has several numberings, and there were some small motor. This was the next project in my postdoc. We added motors also, so that if you are coming from the office, you are coming to the office, and these jet cones actually play around, move around, and they create, along the ceiling, they create different air velocity directions. For example, if this is the room, if I am sitting over here and you are sitting across me, and if I want more air over here, or if I am driving and I'm coming and I'm feeling a bit hot because I'm coming from outside, so I will, through my mobile application, I'll say that I'm feeling hot, I need this much over here at my place, I'm around my desk, right? And these jet cones will automatically, through machine learning, they will adjust their jet cones, and they will create microclimate that I want around me in my desk. This was an idea, and we didn't know that it will be successful or not. So we carried out a lot of simulations, CFD simulations. We carried a lot of experiments. It was a huge project, and this innovation was a new one. This was the device. It is being patented, and we then had, this is basically the concept, that this is the normal chill beam. It has jet cones. If its number is 5555, it means that it is a uniformly distributing air like this one already. But if we just change the numbers, more airflow is toward this side, like 58% toward this side, and rest of 42 over there. So if you just see that if it is in the ceiling, it will have an impact. So it is not the air is not coming directly on us, because we don't, as a designer, we never want to have air directly on us because of discomfort. It is a discomfort. We never throw air on us like fans. We usually have in Spain we usually have fans, or in Pakistan we have fans, direct air on our face. We feel comfortable because the heat is being transferred very rapidly, but it is not comfortable. At the same time, you cannot sleep with this fan on your face. So we usually have it around. We have to have circulation in the room. So this was my second year of my PhD. Yes, the same amount of air that is coming. We are just playing with the air. And this is why whole indoor climate research is based on the air inside the room. We don't care about the air inside the system at the moment in the planner. It is a fixed air, that is the fan or air AHU or fan coil unit is being attached. But we have to address the problem. The problem is something else. And we are not having a fan, it is the air, it will move over here and it will throw on me. No, it will be using the proper principle. So it will be through ceiling, it will be coming, it will be creating temperature around you. And this is what I have results to show you. I mean, so anyways, along with it, 0.6 meter of active chill beam was used in our research, and they were having jet cones. We made a small experimental study first. We created simulations, CFD simulations. We created a jet. This is how we do simulations, with a very simple geometry, not with a complicated, I mean, creating the whole unit. So we just created a diffuser sort of a thing. We didn't created a pure active chill beam or induction. These were several geometries that we used. It was having like a mesh of like up to 90 million. Even there was a huge computers that were used, because it was a very small elemental size and velocity we were measuring at different points in the room. And it was according to the Finland standards. It was because we say it as Finnish standards. Finnish is very popular with the indoor climate, even healthy buildings, and there are many research. Even it was happening in India this year. So they all deal with endoclimate. So Finland actually has several standards that are accordance with the Scandinavia and all this. So we created this like for 3 different setups. Like there were different heat release, there were computers and all these. These are experimental, these are simulations. We haven't gone into experiments yet. We created a CFT setup for people, maybe for the students who actually believe in CFT, who will be studying or will have studied CFT. So CFT in ventilation is also very important. So in order to save the cost, in order to go for directly to the experimental study, we started if it is possible or not. First, we were not sure about if it is possible or not. Frankly speaking, we cannot contain the air to one place. It's very difficult. It can cross and it will just on a single motion, it can just wrap up the whole system we are working.
Yeah,
So I have shown you, all of my students even over here, I have shown you that how complex the system was active chill beam. But in CFD we made it very simple, just a diffuser, because it is how it is.
it looks simple.
Yeah.
It looks simple, but when you are actually into it,
Yeah.
then you get the impression that how difficult it is.
It is very difficult. I mean, so there is a lot of physics behind it. I mean, there are simple algorithms that we use, numerical algorithms. Why we didn't use any other approach? This was all because of, I told you there was a guy with me who was my supervisor. Another, I give him the credit. He actually was a master. He introduced CFD in buildings. Peter V. Nielsen. He is the biggest name in whole world on CFD in buildings. There is no other guy near to him. Even if you write on Google Scholar Google, you will know what I'm talking about. He introduced CFT. I mean, this all is being happening because of him. Anyways, so we, after having CFT results, we conducted experiments. You see that it very much close to the geometry that we made, and it was having like dummies. According to dummies, we didn't created a mannequin, like a actual mannequin. We created very simple so that our CFD is easy. We introduced electric bulbs inside so that heat is being released, like 64 watt per area. And similarly, we try to make it similarly for bigger and bigger setups. And you see the chill beams at the ceiling. So we created indoor climate study through experiments. This was actually the instruments we used. It was anemometer, simple bulb-shaped anemometer through Dantec, and it was not any out of the we use over here too. I think so. Anemometers for measuring velocities. So we hot bulb anemometers were used in the study for air velocity and temperature measurements, and they had an accuracy up to 2%. The criteria that we used, maybe I'm not sure over here we use any criteria or not, but in the world we use for thermal comfort, we use PMV and PPD criteria. PMV and PPD, you can see from the graph that PMV have certain values, we have formulas for it, and we add temperature velocities inside and we get the result. And if it is between minus 0.5 to 0.5, it means that you are in a comfortable zone. And you supply also air velocity. Now there are simple calculators even for ASHRAE. The PMV calculators are a bit different. They need, as I told you, they have, if we say that 0.15 velocity is good for me, but ASHRAE will say that 0.2 velocity is good. I mean, this is a difference, but it is not a huge difference. I mean, so we use PMV criteria to evaluate the temperature and vertical symmetry and all this. So these were measuring points of the where I actually placed the sensors. These were the top view. You can see these were 2 mannequins, 4 mannequins, and there were different points. And at the vertical level, there were also, because as a height of a person is 1.8 meter, and if I am sitting, I will have 1.4 meter. So even the ASHRAE and also these standards also tell that you have to, when you are measuring thermal comfort, you have to measure at specific heights, like for at the level of face, at the level of stomach, at the level of foot. They don't say that randomly you can measure. So it was all according to the standards that we were doing. So results, we got results from CFT and experimental. They were around, I can say that 5 to 10% difference between. And in indoor climate, when we are talking about CFT, up to 15%. For example, I just give you an example. 0.15 velocity has a 10%. How much it is? It's very low. 0.1%, 10% is very low. So you can neglect that difference. So they were actually very good results. I mean to say that, and the results, these were the results of CFT, where I had a very huge mesh in millions. And these were the mesh sizes that we used. We carried out mesh independence test on our computers, on our supercomputers through Cloudia. These computers were actually not in Denmark, these were in America, while I was in America. So these were being used over there. I just show you the example. Then we have the visualization. There are 2 techniques to visualize. You see that smoke over there on the right side. So why it's not working? So if the smoke comes out, I just tell you through visualization that maybe I'm not sure. Yeah, it's they're working at the same time. So they are all at like they are like conventional way is that it comes down straight, but over there you can see that it's moving towards the other side. If I just repeat it again, just for actual visualization now. So the smoke, you see that it should be coming down, but it is coming towards the right side because I have changed the position of the jet cones. It is pushing towards the right side, and then eventually it becomes the same. But we can move that through changes over here in the system, and over here it will also play, I think so. And it is coming. It's an example to show the conventional and non-conventional means. So it is inside the lab I was using, and the video, and in order to put the smoke inside just to show and visualize that this is how it was working, and we had several points for measurements. And over here you can also see now the smoke is being coming out of the this, and over here it should come down very straight. It's very straight. So this is a conventional, and it is a some innovation over here. So this as a picture just for a very small smoke coming down. It comes down and it spreads. This was a new things that were coming out during the study. This is not my objective, but we were looking at the flow, what was happening with the flow. And if I get some good results, then what I will do, I'll just publish. So I just publish another one. So I think so this was in I don't know, this paper was published in Proceedings of 17 International 30. It was indoor area. It was indoor area in Finland, in Kuopio. I presented this research, and this actually colliding jets were seen over here, and this showed that rounded inlets to have spiral airflow patterns, and for simplicity induction feature was ignored in the geometry and all this. So these were actually the things. Then the results, I just quickly go through the results. It's I think so quite late now. So precision ventilation with one chill beam, I showed you the model with one device. It was these results. You see in the CFD profiles. So these are CFD profiles. So you see that both zones with 1.2 metabolic rate, both people are very happy with 1.2 metabolic rate. Temperature variation between 20 to 26 are used, and then table on the right shows PMV PPD. So you see that there is no problem with anyone over here. Both are at the same level of metabolic rate, 1.2. Like I am, you are both at the same. But then I created 1.2 for one person and 1.4 for the other. This means that 1.4 needs more air. So my CFD results, that the transient time of my CFD showed that it can be possible to have from this system, you can create 2 microclimate. This was the proven thing for one chill beam. But it was very simple that if you have a one room, one is high, one is low, it is very simple. But the challenge was having big offices. Open plane offices are always big. It's not only singular office. So this was for 1.2 and 1.6. Studies showed that it can be vary up to 1.6 when a person is sitting. So we had more airflow towards the other side where there was one airflow. These were the PMV, PPD according to different temperatures. It all lied. You can see that in a comfortable, when we measured the PMV values, they all lied within minus 0.5 and up to 0.5. So they all lied within the comfortable and satisfactory ranges according to the PMV criteria. So for one chill beam, we got successful, and then we published another article. Because this was actually the thing we proved, and this was a general article. This was my first PhD and second PhD article, and then it proved that precision ventilation, the first time I introduced this term, the precision ventilation in open plane office, a new application of active chill beam with JetCon. So this is how we were moving. So it proved that with one chill beam I can achieve microclimate in a room, in a small room of 12 meters square or 16, I think so. Then we came to multiple chill beams, 2 chill beams, and then the colliding effect was moving here and there. This is a singular plane I'm showing. It is a 3D model, but I'm just placed it. So you can see that I can use also the colliding airflow. You can see the red area. Red area has a velocity up to 0.6 meter per second, but I need velocity 0.15 for 1.2 metabolic rate until maybe it is for 1.4 and 1.6, I need velocity for 0.4 around me and 0.65 or 7 around me when I have a higher metabolic rate. So I saw that colliding jets that we studied before can be make use and can be used to create microclimate around, as we have shown, we have seen in the smoke test. So we carried out several cases. You can see that this was an ordinary case, like it is like all people are at the same level of 1.2 metabolic rate. It is supposed to be that this area where there is a colliding jet, it will have a higher air velocity. Rest of them were having normal air velocity at the foot level. This plane is at 0.1 meter from the floor, and the other plane is 1.1 meter at the level of your face. And then we saw that how much velocity is around it. Similarly, we just had another cases when they were 1.4 metabolic rate, and then they were 1.6 metabolic rate, and then we changed the arrangement. Like, it is not necessary that two people over here are with the same air velocity. It is possible that this one has 1.6, this has 1.4, and these two has 1.2. It can be a cross arrangement. So even though it worked through simulations, and then we had it and then we created CFD for that too. All these were tested with experimental results, this all, and they all were actually they all were tested with and then we also measure the temperature gradient, because it's also a part of thermal comfort. We have to also see the temperature gradient. It should not last more than 3 degrees between the ceiling and down. It should be delta T should be 3 degree. It should not be more than 3 degree or 2.5 degree delta T. So it was very uniform pattern, even though we were playing with the air circulation in the floor. We had another article, precision ventilation of a study of variable jet interaction. We use this jet interaction in order to achieve precision ventilation technique. So this was for 4 chill beams, as we had, and last model was 4 chill beams for multiple. It was a very heavy simulation. It carried out, like, single simulation carried out like at least 9 days consecutive simulations were carried out. 9 consecutive days of my computer was running for running simulation for one model. So you can see that how much computational it is required. So they had the results. This one you can see several. It got successful too. I mean, you can see at the ceiling level, at the ground level, and at the mid level, they were getting proved. PMV, PPD also proved the same results. This was all simulations. This actually proved that experimentally and through simulations we can achieve precision ventilation inside the room. We can create microclimate inside for a person for higher metabolic rate, lower metabolic rate, for a different variation. This actually proved this thing through experiment and through we are for ventilation. We actually, in this study, we didn't specifically just mention that this is also hold for 4. In research, we don't do that like this. In this research, we actually developed another article. It was published later on. It's not mentioned over here, but it was published. We created, like, for example, you create a new product and ventilation strategy. You create a design criteria for that. We created a booklet for that, and we published it for precision ventilation. We carried out some energy calculations that are very common calculations. It was a software PSIM. We use that software. It's self-made software in a department of built environment. Though when I was enrolled in PhD, it was a build. It was called as Danish Building Research Institute, SPS, Stanton's Building Institute. It's Danish word. And then I was moved to Aalborg University. It was Department of Built Environment. And the energy calculations also showed that we changed the temperature from 23 degree to 25 degree, and it saved energy up to 15%. As I told you in the start, we can save energy while increasing the temperature. There is no other way of saving energy in this research, at least. So this was actually the just what we actually carried out. These are the parameters we actually inserted for measuring the velocities. This was the article. We actually, the one I was talking about, we actually created establishment of design criteria for precision ventilation in open plane offices. We actually, in this article, we created the physics behind that this thing holds true, and this was being published into even magazines. There is a organization, maybe you know, Rehva. Rehva. Rehva is a very popular organization. My professor is the president of Rehva at the moment. And this organization doesn't publish scientific stuff. It publishes, like our maybe HVACR magazine saying, it publishes commercial products. So this was also published over there. Anyways, this is actually the another thing that we actually came to know. We were having some limitations too. There were some limitations in this research too. Conclusions were the same, just one slide. Precision ventilation system effectively establishes microclimate zones for occupants with different metabolic rates. We proved it through experiments, through simulations. Higher air velocity up to 0.7 meter per second were created for occupants with higher air velocity requirements. There can be a reason for metabolic rate, can be reason of clothing, and any other reason. You can create microclimate inside the room. And then the vertical and temperature velocity also were all cases were acceptable limits. There were some limitations, as I told you. I will just quickly just show you that for single zone there were some problems when they were creating a single zone. There were some problems with the single zone, but they were when there were multiple chill beams. We just when we were developing the application and motor, it was through machine learning. It was solved. That problem was solved. This is a very old research I'm telling you, or like 2 years back. Then we had a machine learning model, and through application now it can be controlled. Limitations, as I told you, in this research, precision ventilation technique is used to improve individual thermal comfort occupant different metabolic rate. We only carried out research for metabolic rates. We didn't carry out research for clothing. There's clothing factor, usually you add it. So we didn't carry out for that. And then there was, it was not carried out for actual scenarios. For example, if someone opens up the door, what will happen? It will just but we have proved it through Next. We proved it. This is just the research I'm talking. We proved it. It is being implemented to 9 buildings now. Yeah, because it's machine learning now. We left the research over here, and then the machine learning was doing everything. We calculated everything. We gave them the results. So just one more slide. What actually I am doing and what we are doing actually at the moment. We are creating there are 2 grants I have Alfoske. We are developing a smart lab between Denmark, Copenhagen, and Princeton University in USA. We are developing mini sensor. This sensor is being used to calculate water flow, but we are using it for air velocity because the size of that sensor is very small. And we are even concerned that even if we use it in any duct, for example, 60 or 100 size duct, if you put a sensor inside, if you put an anemometer, it will have a lot of pressure losses, and it will have an impact on the distribution patterns inside the air terminal device. So we are developing this sensor, and then we are also using floor dampers. The damper that we are using, we have named it as Easy Flow Dampers. It is being funded by Danish Innovation Fund, and they actually control through the mobile application. Altering. These are some pictures just for the interest. For several, we are carrying out experiments at the moment. These are CFDs that I'm also running for them. You see the sensor. This is a CFD of geometry of the sensor. It's small, very small. It's just like you see that 8 millimeter. 8 millimeter is the sensor size, and the hole over here, it measures the velocity. And you see that I have done CFD for that. We are actually also having a so. These are references, all I have quoted so far, and your time.
Very impressive.